Hi everyone, my name is Jinso Lee and I'm a PhD student at Georgia Tech. Today, I'll talk about our paper titled Gradients as a Measure of Uncertainty for Neural Networks. Deep neural networks have achieved significant improvements in many applications, including object detection and semantic segmentation. These advancements have led to deployments of learned networks to solve real-world problems. However, there are limitations to the current state of neural network applications. Neural networks are prone to failure when deployed in real-world environments that are different from training conditions. So for example, let's say a classifier is trained with handwritten digit images of 0 through 5. But if the classifier is given an image of a dog, the prediction from this classifier will not be reliable because it will still predict it as one of the digits. Another example, a classifier is trained with objects of no challenging conditions or issues. But if it encounters an image of an object obtained via dirty camera lens, the model prediction may not be trusted. To ensure a level of reliable performance, a neural network should be able to identify these types of unfamiliar inputs to prevent from making random predictions. To do so, we need to understand how certain a model is with given input. So in this work, we propose a simple yet effective method to measure model certainty of deep neural networks. Let us define some terms to start with. Given any single architecture, the set of possible models is defined by all possible configurations of its parameters. So the space where the set of model is defined, we'll call it the space of models. So for example, if an architecture has two parameters, its space of models would be two-dimensional. So here is a visualization for the space of models for an architecture defined in two parameters, therefore shown in two dimensions. The loss manifold for this model, however, has one more dimension because there is a loss value associated with every possible configuration of the parameters. The idea of gradient-based optimization is that it aims to find an optimal solution on the space of models by optimizing in terms of loss function. Here's a basic gradient-based optimization setup. During training, the model parameters get updated based on the gradient. So the amount of update is the magnitude of the gradient scaled by learning rate. This also means the difference in parameters between the old and new models. So it can be interpreted as the distance between the old and new models on the space of models. Let's think about model evaluation. Given a trained model, we can still compute gradients for an input in the same way as in training. It's just that it will not be used for an actual model update. So the magnitude of the gradient here means the amount of update required to represent the given input properly. So you can think of it as the distance between the current model parameterization and another model that performs better for this specific input. So we propose to utilize gradient magnitude to quantify the uncertainty of neural networks. Here, by uncertainty, we mean model uncertainty. It's the uncertainty in model parameters due to limited data and knowledge. The gradient magnitude would be small if the model is certain about the input, and large if it's not so sure about the input. So how do we utilize the gradients for this purpose? Let's say there is a classifier trained with these two classes, dog and horse. When the classifier is given an input image and its corresponding label, it asks the question of, have I seen this before? It's seen both the images of dogs and the label dog. So it associates already learned features with the trained label. But if the classifier is given a familiar input image with an unfamiliar label, it doesn't have to learn features again. It only needs to associate the already learned features with the new label. But if the model is unfamiliar with both input image and the label, it has to first learn the new features from the image and then associate them with the new label. So we introduced this concept of confounding label. A confounding label is a label that is different from ordinary labels on which a model is trained. So for example, in this scenario, we can think of the label car as the confounding label since the model is only trained for dog and horse. So the idea here is that the amount of change required to associate a confounding label car with familiar inputs would be smaller than with unfamiliar inputs. Confounding labels provide a way to probe the feasibility of a model in an unsupervised fashion. Just to reiterate before introducing our framework, the hypothesis here is that it takes less amount of change to associate confounding labels with familiar inputs than unfamiliar inputs. So how do we actually utilize confounding labels to generate gradients, which then can be a measure of model uncertainty? Let's say we have a trained model. Given an input, we can get a prediction from the model. Between the model prediction and a choice of confounding label, we can compute the loss. Here, we utilize binary cross-entropy loss. By backpropagating this loss, we can generate gradients for each set of model parameters. We take the squared L2 norm of the gradients for each set of model parameter, and then concatenate them to represent the given input. This gradient-based representation is used to train a binary detector of two fully connected layers as an unfamiliar input detector. Here is a preliminary experiment in out-of-distribution detection setup. We train a ResNet-18 model with MNIST dataset and collect the gradient information by using a confounding label on MNIST test set, as well as other datasets of different domains, including SVHN, CIFAR10, Tiny ImageNet, and LSUN. Here's an example comparison of gradient-based representations for MNIST as in-distribution and LSUN as out-of-distribution datasets. Here, the x-axis shows the network parameters of ResNet-18, from the first convolution layer on the left to the last fully connected layer on the right. The y-axis shows squared L2 norm of gradients, representing the distance on the space of models. The values are averaged for each predicted class for a more clear presentation. As you can see, the range of squared L2 norms of gradients for the out-of-distribution dataset is far larger than in distribution dataset. Here is a more inclusive example of multiple datasets. Each plot represents a different set of model parameters within the network. The squared L2 distance in the model space is a lot larger for out-of-distribution datasets. The range of values for in-distribution dataset is highlighted in the red circle. So the question here may be, why not just use the loss values instead of having to generate gradients with them? Gradients and loss are intertwined in the process of backpropagation, but the loss is computed only with respect to the final prediction of a model, and it's limited to a single value per input. On the other hand, gradients are of higher dimensions, preserving more information regarding the input and the model's current state of each parameter set. Here, we compare the range of loss values for in-distribution dataset to those of out-of-distribution datasets. You can see that the range of loss values for in-distribution dataset rather overlaps with those for out-of-distribution datasets, which means that the loss value alone would not be as effective of an indicator to differentiate the distributions of datasets from the model's perspective. We validate the proposed gradient-based representation as a measure of uncertainty on out-of-distribution detection in a larger scale. We utilize CIFAR10 and SVHN datasets as in-distributions, and then the rest as out-of-distribution datasets. The performance was evaluated in terms of detection accuracy, AUROC, or area under receiver operating characteristic curve, and AUPR, or area under precision and recall curve. We compare our method with other widely used out-of-distribution detection approaches, all based on activations. Compared to other methods, our gradient-based method performs better for most datasets. It shows particularly better results when SVHN is used as in-distribution dataset, and it is due to the domain difference. SVHN is a simpler dataset consisting of strip view house numbers, compared to the rest of the datasets with objects and natural scenes. So it will require larger updates to be made to the model when it encounters more unfamiliar inputs. On the other hand, CIFAR10 as in distribution shows slightly decreased performance for tiny ImageNet compared to the other out-of-distribution datasets. It shows that those two datasets share more similar features as object recognition datasets than others. The model trained with CIFAR10 is more familiar with the images of objects rather than the scene or digit images. So it shows the required changes to the model to be smaller for tiny ImageNet, which were not as effective for distinguishing it from the training dataset CIFAR10. We further validate our approach in detecting corruptions in images. For this purpose, we utilize two datasets that include multiple corruption types and severity levels. CIFAR10C is a version of CIFAR10 with different types of corruptions, and QRTSR is a traffic sign recognition dataset with different challenging conditions. We compare our method with Mahalanobis' method that outperformed all the other methods in the literature for out-of-distribution detection. We also utilize AUROC scores for comparison here. For CIFAR10C dataset, it shows a pretty saturated performance for both methods, but our gradient-based approach outperforms the Mahalanobis method for all corruption types and levels. For QRTSR dataset, though, the results are more interesting. It shows that our gradient-based method is more effective in characterizing corruptions, even at lower severity levels for different challenging conditions. In conclusion, we introduce an interpretation of gradients in the space of models from a perspective of model uncertainty. We also propose a framework for efficient gradient generation with confounding labels to quantify uncertainty of fully trained networks. Finally, we validated that the gradient-based uncertainty measure outperformed activation-based features in out-of-distribution detection and corrupted input detection. Thank you for your attention. For more information, please check out our paper, website, and GitHub.